imagine, but we could do anything under the stars. So good, I eat you. Take me for a ride in your sweet delicious perfect little mouth. Thereupon I linger, where you will have no doubt that I do my best for you. I do. Ah, yeah, let's stop and get it gone. I lost myself just thinking about the two of us from each other, drinking, thinking with our lips. Fingertip and kissing, you turn me inside out, but I do my best for you. Down we go, from the top he pushed me. It is such a thrill to be lost in love and dancing. Shake your tambourine, you blow my head over. One thing is for sure, that I do my best for you. I do, you know, for you I would crawl through the darkest tunnel. I would climb the castle wall. If you deny Rapunzel, let your head down, right in through the window. Look, they lock the door, 'cause I do my best for you. I think the world of you with all of my heart. It's blood through my veins for you. You alone have all of me. I give my world to you. To you all will be true. Oh, it's too good to be real. The smell of something cooking. You're my soul to steal. And all the food of love worth it. What you've given me, for it there's no measure. One thing I'm sure, that I do my best for you. I think the world of you with all of my heart. I do. It's blood through my veins Thank you very much, y'all. Good night.
Alrighty. How's everyone doing? Alright, so today we're going to be going over chapter 2, which is all about force vectors. You can open up your book if you want to. I'm just going to be following what it talks about in the book and going over it, and hopefully from what I say you'll be able to understand it better, seeing as of right now we have no real way of keeping in communications with the professor, as the professor just kind of, is not understanding how technology works. So this is how it's going to go. First thing that we're going to talk about are scalars and vectors. Scalars, I apologize, are things that are, they're things that are only determined by their magnitude. So it can be a positive or negative quality, but it is only defined by like how big or how small it is. So for example, an example of a scalar mass would be length. The reason why length would be an example of a scalar mass is because length doesn't have any form of really, it has no direction. Length is just, yeah, like that shoe is a foot long. That pipe is 2.5 feet long. There's nothing that really says that there's no direction into it. And then vectors. Vectors are a little bit different. So vectors are a quantity that have both a magnitude and direction. So a good example of that would be something like distance from a point. So let's say, for example, you're trying to find the distance from a point, and let's say you're on a one-dimensional plane. So you're here, and the point you were trying to find is over here. So there. Now, if it's one-dimensional, it's technically scalar because you don't have to worry about direction. It's just, is a positive mean going to the right or negative mean going to the left? Vector quantities, on the other hand, that is when you start looking in direction. So let's say you're on a grid, and let's say you are right over here. You're trying to find the point over here. And yeah, there's the distance, that's your magnitude, but then you have to find the direction. So the direction would be given as an angle, whether you want to do that in radians or degrees, that just depends on the type of problem and the type of response needed. And the way I'm going to be labeling these going forward, anything that I do that is going to be a magnitude, I'm going to be writing it in capital letters. And if it is a direction, I'm going to be doing that in lowercase or adding some other way to define it. So let's do it. So that's how I'm going to be writing out the two for this. The one thing you have to remember with this is scalar quantities are only how large they are, how small they are. They can be positive or negative, whereas vector quantities have both magnitude and direction. So you also have to worry about position or the angle. Now let's talk about vector operations. So you have a vector, and let's just say a vector, and let's call it A. The way vector operations work, if you are trying to double a vector, if you're trying to double specifically the scalar quantity, so magnitude, if you're trying to get 2A, all that means is you are doubling the length of the vector. You're not changing the position. All you're doing is changing the length or the magnitude. If you, let's say for example, you're trying to do negative A, so A in the opposite direction, you don't change the two endpoints because technically, whenever you're doing a vector, there's usually some form of start and end point. All that negative A means is that the direction is reversed. So it'll have the same 2 points. It's just that the start point and end point are flipped. And then if you're doing negative 1/2 A, so you keep that bottom point. You keep the bottom point, and that'll be, in this case, that'll be the end point. And then, so you go half, and so it's half the distance because it's negative. You flip it around. So the things to remember. The things to remember when it comes to scale multiplication and division are multiplication, division, you always keep your endpoint. You always keep your original endpoint. You always keep your original endpoint. It doesn't matter whether you're multiplying or dividing it, whether it is a positive or negative. You always keep this. This original starting point you keep no matter what, unless, well, you'll see later. But you always keep the original endpoint. And if it's negative, you flip the direction. And that's all that things like vector addition and just scale multiplication and division. That's all that means. It's really all that there is in that. Then what we're going to be getting to next is vector addition. So vector addition is when you start getting into like adding 2 vectors together to find something. So let's say you have vector A and vector B. And let's say that you want to add the 2 together. What that's going to do is going to create a resultant vector that reaches right around here. What happens is you're following a law that you probably used earlier on in math courses, but in a different way. It is called the parallelogram law of addition. All that means is the resultant vector that is created. So right here, this will be the resultant vector, and this will be kind of finishing off the parallelogram. But this resultant vector is called R. All R is just R equal to A plus B. Now in this case, A plus B does not mean the scalar magnitude, it means the vectors themselves. The reason why is because let's do this. So if you're trying to do the resultant vector, you would follow what's called a triangle line. So in this case, R would be the hypotenuse, A would be one of the two smaller sides, and then B would be the other side. You're just at that point you were just starting to follow basic trigonometry, which at this point you probably should know. And and this is all that really happens. And then again, if you're trying to do something weird or wonky, like let's say you have an A and then you have a negative B, that just means that instead of the direction that, direction for this is there. All it does. There's nothing really wonky there. Now, in this case, when you were trying to find those resultant vectors, in this case, so let's do a little bit. So in order to find the resultant vector, what you're going to be using are the sine and cosine laws that you can learn, hopefully, back in geometry or pre-calc. So in this case, you have, let's rewrite this so that way it's a little bit easier to understand. So because that was essentially following the triangle law, but just to make it easier to understand, let's rewrite it as a triangle. So you have A. So this would be side A. This would be the scalar quantity. This would be side B, and then side R. Then you have angle B, angle R, angle. Now, what the sine and cosine laws mean is, in this case, it would be R is equal to the square root of A squared plus B squared minus 2AB cosine of the angle C. So in this case, the angle R. That is what the cosine is, and that's how it applies to this specific triangle. And then what you will also use is what is called the sine law. The sine law just means that A, so length A, or magnitude A, or angle A, or the sine of angle A, is equal to magnitude of B of the sine of angle B equals R, magnitude R, over sine of the angle R. So you have your sine law, and then your cosine law. That's really all that there is to it when it comes to finding a resultant vector between, when you're trying to find a resultant vector in the half table. Because remember, we're still following parallelogram law. I just cleaned up a little, so you still have that little like this. Well, really, we should be over here, but hopefully you get the point. If not, I do apologize. So let's go ahead and do a couple example problems in the book. So at this point, I'm on example 2.1 from the book. That is where I'm at if you're following along in there. If not, that's fine. Works out away. So we have a screw eye, which kind of looks like this, but the drawing is terrible. No, let's try that. they have screw eye. So screw eyes kind of just close enough. And just to make things clear later on, let's just make that within a 90-degree field. And then you have two forces acting. You have one right here, is at a 15-degree angle from this bottom. And this, which we will label as force 1, has a total force magnitude of 100 newtons. And then force 2, which is going to be up here, has an angle of 10 degrees. And force 2 has a magnitude of 150 newtons. So, what we are trying to find is the direction and magnitude of the resultant force. Now, how do we do that? Well, first off, we complete the parallelogram. So I'm gonna erase that just to make it a little bit before we move on to the next. So you have the two angles, and you can probably guess the resultant vector is going to be here. So let's just put that there for now. And we're following the kind of parallelogram law. So we have this. So this is kind of like the ghost that finishes off the parallelogram. So this in total is equal to 90 degrees. In order to find these two angles, what you have to do is you add the total of these two, so the angle of force 2 and the angle of force 1. So let's see. Yeah. So all you're doing in this case is we're taking 90 and then you subtract the two angles. And this nets you 65 degrees. And when you have the 65 degrees, then you're able to find the angle of these two on the parallelogram. So in this case, what you do is you take 360 degrees minus 2 times the angle that we found, so in this case it would be 65. Divide all of this by 2, and what we end up with is that the angle at that point would be 150. Now, the reason why we needed that 65 and the reason why we got that 115 is with any four-sided shader, no matter what it is, you are going to have a total degree count of 360 degrees. And we already know that these two angles right here are 65 degrees. This is the parallelogram, not some oblong shaped shape. So we have these two, and we did this in order to find their magnitudes. So these are 150 degrees. So what we can do at this point would be, we start off by using the cosine law. So remember, cosine law is the magnitude of the resultant force. So let's go ahead and write that as F bar. R is equal to the square root. It's going to be the square root of a squared. So in this case, that would be the 100 Newton force. So the force 1 would be 100 squared plus, so plus 150 squared minus 2, 100, 150 cosine of 150. The reason why is because in this case, this would be the resultant vector, and we're starting to look at this as a triangle again. And this would be the angle R. 115 would be the angle R. So that's why we put that there. Then I'll let you try and do the math on your own. But what it comes out to is that if you round it to the nearest tenth, you get that the resultant force, which is F of R, equal to 212.6 newtons. That is the resultant force, and we now have one of the two quantities needed. And all that's left is to find the direction. So, okay. So, at this point, we have our resultant force. And at this point, all we need left is our direction. So, I'm going to go ahead and just take all this off. So we have room for this next one. This next part is where we get the direction of the resultant vector. So what we do here is let's redraw. So all right, sorry about that. That should be good. I apologize for that. So at this point, let's rewrite that last half. So at this point, we'll have the triangle. Remember, we're still part of that. Still part of that kind of like ghostly 90 degrees. We still have a 50-degree angle right here. And then you have this. And then this angle right here. So this angle right here would be theta. And then this one right here would be phi. Remember, I put in Latin correctly. So remember, this line right here is the 100 Newton force. And then this one right here, because we were doing the law just for finding a resultant vector, the force, or just the vector in general, the second vector, which would be F sub 2, is going to be 150 newtons. Remember, we have this angle. This angle is 150 newtons. So, what we have to do is refer this to the angle we want. Phi is the angle that we want to answer this question, but we can't find that until we find theta. And the way we find theta is by doing the law of sines. The way the law of sines applies here is, remember, for each side, remember just that. So, we first have, let us put the resultant force, so that would be 212.6, put it over the angle of the resultant force in the triangle, at least. In this case, it would be the sine of 150 degrees. And it's equal to, in this case, 150 degrees, or sorry, not 150 degrees, 150 newtons over the sine of theta. Because remember, we're doing like a cross. So even though it doesn't necessarily look like it's a cross, it's still what it is. So what we now have is just equal out the sides. We now have the sine of theta equal to 150 over 212.6 times the sine of 115. And you can go ahead and do the math on your own if you'd like, but at that point, we end up with theta equaling 39.8 degrees. give or take, because it's always rounded. So what you do at this point, in order to find phi, and hopefully you can see from even my lackluster drawing on the whiteboard, hopefully you can see that phi is just the angle from the first vector added to theta. So all we do to find phi is just add the two together. So we have phi is equal to 39.8 times 15 degrees. We find that phi is equal to 54. So it is equal to 54.8 degrees. So I'm just going to move that off the board. We have now found both ends. So let's just put it all together. So we were originally tasked with finding the resultant vector. Found the two individually, so how do we write it out? The way that we write it out is this. At least in this situation. So in this situation, the way you write it out would be the force of the resultant vector equal to 212.6 newtons. The angle of the vector, the direction of the vector, so in this case, let's do phi sub r equal to 54.8 degrees. And that would be how you write it out. Now, let's keep moving. Let's see what we got left. Okay. So all that's really left to talk about is just a couple more examples. So, is there anything that anyone wants me to go over personally? If not, that's fine. Then I'll just pick one out. But feel free to tell me if there's any that you want me to look at specifically. Let's see. I don't think anybody wants to come in, so let's go ahead and do one more problem. Let's see. Let's take a look at example 2.3 from the book. So, I erase that. Get rid of that space. So over example 2.3. Example 2.3, we have just essentially like a dot. It vaguely looks like a pyramid, but it doesn't matter. We have forces acting on here. So let's go ahead and draw that. Goes to y again. So we have that again. And then we have the two vectors in between. So we have first off, we have the resultant force of vector 1. Okay. So vector 1 is 30 degrees. 30 degrees. And it has a force of 200 pounds. And then we have the second force, which this one, a little bit more fun. This one, we have the second force over here, 45-degree angle from positive. 45 degrees here. But we have no magnitude attached to it. We don't have a magnitude attached to it, so what we have to do is we have to find the magnitude of force 2 along with the magnitude of the resultant force. So let's just label that R. And on the question, it tells us that the resultant force is along the vertical axis. So it's the positive y-axis in this case. So let's start redrawing this out. So let's just kind of complete the parallel. So let's see. So this angle, so this in total, because we have the 60 degrees here, so this angle and this angle in total are going to be 105 degrees. What's that going to be? So we have those. And then the way we find this angle now is, fortunately, we can just actually add these two together. So these two are both going to be 75 degrees. Now we have parallelogram. Now, what we have to do now is kind of just slow it back up and turn it into a triangle so we can actually figure out things. So let's transfer it over here. So, triangle, and we know that this angle is 75 degrees. Now, we know that this right here is we know this angle here is 60 degrees. Because we know that's a 30-degree offset, and because it's just going straight up there, it's just kind of simple. It's just, we know it's 60 degrees. Now all we have to do is to find the third one, which we just subtract 75 and 60 from 180. And what we get there is a 45-degree angle. We have a 45-degree angle. Now, what we have left, we have the force, or the magnitude, vector 1, so it would be 200 pounds. Then we have undetermined force from vector 2, and then we have the force of the resultant vector, R. Now, the way we find these two is we use the law of sines. You remember the law of sines is each side, if you take their magnitude and put it over the sign of the direction, it will all be equal to each other. So all we have to do is just match them up. So 1, 2, and 3. So what we can write over here is just, we can just write out 200 over the sine of 45 equal to half sine of 60 equal to r over sine of 75. Okay. And at this point, just make a little inner. Let's split this off. Just make a calculation here. So we'll do 200 over. So what we do, all we have to do over here is get f on its own. And that just turns into f equal to 200 times the sine of 60 over sine of 45. In this case, we calculated it all out, and I will do that right now because I just was just coming with on a calculator and doing all that. So f, when you go to math, equal to 245 pounds. And let's just so r, in this case, when you get it all done, it's just equal to 200 times the sine of 75 over sine of 45. And the result magnitude that you get after doing the calculation for r is equal to about 273 times. And you have your two solutions to the question. So I'll just erase the page. These are the two answers that you needed. You needed the force of the second vector, so that would be f. So the first thing that they wanted, and then they wanted the force of the resultant vector, which we have. This entire chapter is just basic trigonometry and geometry, but applied in a different way than before. For those of you who have taken Physics 2 or differential equations, you'll most likely recognize this because it's this, along with other things relating to it, are gone over a lot in this class. Honestly, statics is just a more in-depth version of this. All statics is just you're trying to find the magnitude, direction, and vector, or in some situations, multiple vectors that have the net equilibrium, or just an enforcement point, to equal 0. So let's say you have this point here, and let's say from 2 dimension, and you have a bunch of different vectors with different forces. All that statics means is we're trying to find the one force needed to act on this vector, or this point in this case. So let's put it here. In order for the net force, so net force and direction both equal 0. The statics is all about equilibrium. That's all I say. Does anyone have any questions? Now would be the time to ask, because after this, I will go ahead and be ending the stream, and then hopefully it'll be posted on Twitch, and I'll also be manually uploading it to YouTube. So, anyone has any questions, say them now. If not, I will end the stream.